back. Last Wednesday, we talked about the definition of orthogonal coordinate system. So you might have three different unit vectors. Call this U1, U2, U3. I like to add the hat to denote it is a unit vector. So for any orthogonal coordinate system, you would have three unit vectors, and they are each perpendicular to each other. Right? So basically, if you write the stringent formulation in math, would be any two unit vectors making a cross product will be the third one. Okay? And if you make the dot product between any two unit vector, they will be zero if they are not equal, because they are perpendicular, right? So today we're going to look into more details. I want to convince you by understanding orthogonal coordinate systems, all the vector products analysis would be very easy and straightforward. Last Wednesday we talked about the dot products between two vectors, and today let's talk about the cross product. So we have vector A and vector B. They are both expressed using the same coordinate system. They both have the first component in the first direction, second direction, third directions, right? So now you make the product. Ideally, again, you would have 9 terms. But now, because let's look at the first term. A1 is making a cross product with B1. But if you remember, A1 and B1 are in the same direction. So by definition, AU1, the first unit vector, making a cross product to itself must be 0. Because by definition, cross product have to be unidentical. If you make a cross product with yourself, then you would have 0. So by the same analogy, the second element making a cross product with the second element of B2, but in the same direction, would also yield to 0. Third component in the third direction, making a cross product to the third component in the B vector, but in the same direction would also yield to 0. So 3 out of 9 components will be 0. You don't really need to calculate them. So the remaining terms, the non-zero terms, would be the one in the first unit vector direction. Okay? Remember, this is where you really have to think. Cross product gives you a surface, right? So surface comes with a direction and an area. So when your direction is determined in the first direction, then the area must be determined by the other two products. So AU1, the area must be defined by the component in the second and third directions. And if you still remember, cross product, the direction is very sensitive to which two you apply. A2 and B3, A3 and B2 would have opposite directions. Okay? So therefore, for the first direction, you would have 2 components, but they are having opposite signs. Alright? So if you condense all this into a matrix form, A cross B using orthogonal coordinate system will be extremely easy. All you have to write is the first unit vector, second and third, and then A1, the first component of your A vector, second component, third component, and B1, B2, B3. And then you just calculate the determinant of your matrix. As opposed to what you learned during high school, if you want to calculate A cross B, you have to find the angle. right? You have to find the angle, you have to take the sine, and you have to know A and B magnitude. So knowing the vectors and being able to express them using orthogonal coordinate system is very handy and straightforward, right? Now, take a moment and ask yourselves, we already know how to express A cross B vector. Now, let me remind you, A cross B results in a new vector. So now you have a new vector making an inner product or dot product with a third vector. The result should be a scalar, right? Okay, so think about it. How to properly write the matrix form when you have the scalar triple product. A cross B, you would have your first component, right? And then you make the inner product with the first component of C vector. So this results in a scalar in the first component, second component, and third component. So you end up with a scalar value. It's only a value, right? So in matrix form, for the scalar triple product, it's very similar to cross product between two vectors. All you have to replace is, now you just write down C1, C2, and C3. That's it. Okay. So these are very basic fundamental vector calculus, right? So let's move on. Today I want to focus on orthogonal coordinates. Okay. The reason will be very apparent because later we will talk about gradient. I know you hate it, okay? Gradient, divergence, and curl. All these three operations are fundamental and extremely important. So in the past, I know you just memorized the formulas for all three different orthogonal coordinate systems, but memories don't really last. Same for me. When I was a student, I was not able to really memorize everything for gradient formula, divergence formula, curl formula, but today I want to really teach you how to derive. And being able to derive all those complicated formulations relies on your understanding to what I am going to teach you for the next 40 minutes. You have to understand about the orthogonal coordinate systems, its definition, and their resulting differential length, differential area, and differential value. Once you understand all these three parameters for three orthogonal systems, then gradient, divergence, curl are actually very straightforward. Alright? So, the first one is Cartesian coordinate. It's just a common x, y, z coordinate that you guys used for the past 20 years. Okay? So in three-dimensional world, we can define a point using x, y, z coordinate. Okay, so I can express a point using their different x, y, z positions. Okay. Same for a vector. Once you have a position which is being expressed in Cartesian coordinate, your vector can also be expressed using Cartesian coordinate. For example, ax, ay, az in this case, y equals yz, az equals y squared. Okay. So once you read this vector expressed as xy, you know the vector is having some positional dependence expressed in Cartesian coordinate. Right? So the question is, once we express some position or a given vector using Cartesian coordinate, in this coordinate, how do we express the resulting differential length? What I mean is, I have x, y, and z. These are my three different axes. Okay. So if I allow to have some small change, starting from the point, a given point, P, it has x1, y1, and z1, right? All these position grids or values. I allow them to have some small change in x, y, and z directions. What type of three-dimensional object would I result in? In Cartesian coordinate, if I start with a certain point and I allow it to have some offset or shift in the y direction, x direction, and z direction, the result will give me a cubic, a very small cubic, right? So if we look closely at this figure, if we want to start from this location, this point, and we end up at the diagonal point, how should we travel? We should travel in the x direction, right? By a distance of dx, right? So we travel to here, and dz, and then dy, right? So on this cubic, if you want to travel across to the diagonal point, we have to travel by a distance of dx in the x direction plus dy, this is a distance in the y direction, and dz in the z direction. So in essence, if you want to move to the diagonal point on this cube, you have to travel total of these three distances sum. Okay? So the result is a vector. Okay, so this is called the differential length for a Cartesian coordinate. Now, this cubic volume has total of 6 surfaces. Okay, total of 6 surfaces. But usually we only take account of 3, the positive directions. Right? So this is the point I want to ask you. An area or a surface which has a direction of positive x, right, pointing out into your eyes. If I know my small surface, differential surface, is pointing in the direction, in the positive x direction, how would its area be determined in Cartesian coordinate? This is the knowledge you accumulated from cross product, right? If your surface is having a direction, the direction is normal or perpendicular to your area, right? As a result of vector cross product. If the direction is in x direction, then its magnitude must be determined by the length in the other 2 directions. dz. Okay, so it must be dy and dz. So this is what I'm trying to repeatedly emphasize. A surface is a vector. It has its own direction and its magnitude. The magnitude is called the area. Once you know the direction, then the area will be determined by the other two magnitudes. So in this case, you have a surface which has a surface direction in the x direction, then its area must be determined by the differential length in the other two directions, dy times dz. Okay, so let's come back to the PowerPoint. So the other two differential areas would be, if you have a small square in the y direction, the direction is in y, then its magnitude must be determined by the differential length in the x and z direction. So y dx dz. If you have a square in the z direction, then its magnitude, the area must be determined by dx times dy. Okay. This is a direct consequence of vector cross product that we mentioned last Wednesday. Okay. Everything are very straightforward and simple up to now because we're working in the Cartesian coordinate. So differential length, x direction dx plus y direction dy plus z direction dz. Straightforward. Surface, once you know the direction, the magnitude will be determined by the other two differential lengths multiplied together. Differential value. Well, you know how to calculate the volume for this cube. Straightforward multiplication of dx, dy, and dz. Straightforward. Okay, nothing tricky. Now let's move on to cylindrical coordinate. Oh, this is slightly tricky, but you have to remember, my methodology is I'm trying to emphasize differential length, differential surface, and differential value. But before we do that, a formal definition of cylindrical coordinate. When we talk about the cylindrical coordinate, we are talking about some object, cylinder-like, like a tube. Okay? So the points, any point on the surface of a tube can be defined easily by the radius, azimuthal angle, 方位角, azimuthal angle, and z. So z is identical to the z in Cartesian coordinate. Okay? In essence, we are talking about a three-dimensional object with a constant radius, but it can change in height, and then you can change in angle, right? So in the future, the unit vectors, A in the radius direction, I will just write the r hat. Okay? Radius hat means the unit vector in the radial direction. A phi, the azimuthal angle. I can write this phi hat. Z, just z hat. Right? So this is position. You can also express a position using cylindrical coordinate. Then you see a bunch of radius, phi, angle, and z. You can also express a vector using cylindrical coordinate. Okay? So later, once we understand cylindrical coordinates, we can convert or transform between Cartesian to cylindrical coordinates, right? But up to now, let me ask you a simple question. I have ax, ay, az expressed in x, y, yz, y squared, right? If I write the same vector using cylindrical coordinate, I want to express this vector, the same vector, but I rewrite it somehow. So it is defined using cylindrical coordinate. what would it look like? The question now is, how to properly transform the vector into cylindrical coordinate. If you want to express this vector using cylindrical coordinate, you don't expect to see x, y, z, right? X, y, z are products, are results of Cartesian coordinates. If you express the vector using cylindrical coordinate, you would only expect to see r, phi, and z. So z is allowed, but you don't allow to have x and y. In cylindrical coordinate, you only allow r, the radius. You only allow phi, azimuthal angle, and z. Okay, so we have to learn somehow. But before we do that, let's have a clear understanding to differential length, differential area, and differential value in cylindrical coordinates. So if you start at a certain point on a cylinder and you allow to have some differential changes along the three unit vector directions, you would end up with this type of three-dimensional object. It's like a pizza when you eat the inner cycle first, right? The remaining of your pizza is like this. It's I don't really know how to call it. Really? I don't. Okay. So again, the question is, how can we walk from one point on this three-dimensional object to reach to its diagonal point? So we can start from this point and we walk along this path. So we initially have a initial radius, and then we increase the radius slightly by dr, right? So we walk from this point to this point, then we have r plus dr. And then we can change our height from z to z plus dz. What does it take for us to walk from this point to the final point? From here to here, are we walking along a straight line, or are we walking along an arc? This is a crucial point for you to remember, and I also noted on the PowerPoint. When the unit vector is an angle, then your differential length is not a straight line, but an arc. The length of an arc, 弧长, the length of an arc is radius dependent. So therefore, you have to remember the differential length is an arc when your unit vector is an angle. So this arc, the length of this arc is r times d phi. So although you have the same angular change d phi, but depending on your radius, the length of the arc will be very different. Okay? So if you want to buy a 6-inch pizza or 12-inch pizza for the same price, you will always go for the larger one, right? Because it's bigger. Right? So therefore, the differential length in cylindrical coordinate, dl, a vector, would be dr in the radius direction plus, remember, when you have the unit vector as an angle, then your differential length is an arc. An arc is radius dependent. So you have to multiply this radius r by d phi. So you have a small angular change, but your total arc must be multiplied by the radius. Okay? Z direction is just EZ times. So the proper way to write down the differential length in cylindrical coordinate, you have to pay special attention. When phi direction is an angle, then the differential length is an arc.